What if you could write a letter to Bernhard Riemann containing a discovery he could verify with 19th-century mathematics, yet which required 21st-century computational power to find? This paper bridges 165 years of mathematical history with a stunning empirical result about the distribution of prime numbers. Let's begin by understanding what makes the Riemann hypothesis so fundamental. Building on that foundation, the Riemann hypothesis posits that all non-trivial zeros sit precisely on the critical line. This seemingly abstract claim controls how primes are distributed, and for over a century and a half, mathematicians have attacked it from every conceivable angle. Now we arrive at the paper's central innovation, a computational thought experiment. The authors employ a striking strategy, extremizing a quadratic form restricted to functions supported on a finite interval, using shockingly few primes. The numerical concordance is overwhelming, with precision exceeding 50 decimal places for the first zero, and remaining accurate even at the 50th. This visualization captures the heart of the discovery. Each computed spectral element aligns almost perfectly with the corresponding Riemann zeta zero, forming a pattern so precise that computational error or coincidence become untenable explanations. The convergence is both visually striking and numerically ironclad. On one side, the theoretical machinery guarantees that the approximating zeros live on the critical line, inheriting this property from the spectral structure of Weil's quadratic forms. On the other, the finite computation becomes feasible precisely because you only need a handful of small primes to achieve breathtaking accuracy. This discovery sits at the intersection of multiple mathematical domains. Prolate functions, originally developed for radar engineering, turn out to approximate the critical eigenvectors with remarkable fidelity, while random matrix theory explains the statistical behavior and geometric frameworks provide the unifying language. While the numerical results are staggering, the authors candidly acknowledge that a full convergence proof is still missing. Yet the precision achieved and the theoretical consistency strongly suggest that spectral and geometric methods offer a viable route to proving the hypothesis itself. Beyond its technical achievements, this work rekindles optimism that one of mathematics' deepest mysteries might yield to a synthesis of classical insight and modern computation. It exemplifies how rigorous numerical experiment can guide and inspire theoretical breakthroughs. In sum, this paper offers both a sweeping historical synthesis and a tantalizing empirical discovery that brings us closer than ever to understanding the zeros of the Riemann zeta function. To explore the full details and figures, visit emergentmind.com.